Greetings, another 342 video lecture. Today, let's review. Last time we talked about how to take some loads and reactions and convert those into stresses. Today we're going to say, well, how do we deal with these stresses, right? So for instance, here I have a stack of paper, right? Just a regular old, it looks like it's some typing on here. Old exam or something like that, maybe a scientific paper, surely fluid mechanics. So if I take this stack of paper and I bend it, right, and I bend it like this, what happens? Okay, well, the fibers down there, the bottom sheets of paper, well, they must have got compressed, right? And the top ones must have stretched. And so according to Hooke's law, which we did in 306 and 307, too much work for one credit. Then when these things stretch, let's see, sigma equals Young's modulus times the strain. So there's some strain here times Young's modulus that results in some stress. So it totally makes sense that when I bend this, I wind up with stress. The stress follows the strain. It's not the other way around. We usually think, oh, you load it up and then it causes, no, it's the stress follows the strain. I think that's just a more intuitive way to think about it. Okay, so here we go, a sheet of paper. It's kind of easy to picture the top pieces of paper stretching and the bottom ones compressing. Well, so here, right, it's summertime. So I've got a swim noodle, wonder noodle, pool noodle, whatever you want to call this thing. And this, actually, it's hollow, but it could be solid just the same. This could be the drive shaft of a car, or the shaft on a wind turbine, or whatever, right? And it's subjected to some loads, right? And so if I bend it this way, it's not as obvious to see different fibers stretching or compressing, but surely the fibers along the top here, right, where it's curved, the concave part of it, the convex part of it up here, would be stretched. Therefore, we expect some tensile stress to result from that. And likewise down here, right, they're going to get compressed. So we're expecting some tension up here, some compression down here, and then that's what causes the internal stresses the normal stresses that result from a bending load. All right. So enough of that. Let's go get into the good stuff here. Where is my Apple Pencil? There it is. I love the Apple Pencil. So we're gonna do a little bit of work with our old friend Mohrs Circle here, right? Which I know you learned about in 306, but most people come out of 306 and they still don't really get it. In fact, come on, camera. My good friend, colleague, Professor Frank. He hates the Mohrs Circle. I'm like, why do you hate the Mohrs Circle? So why don't you just use the stress transformation equations? I'm like, well, every time we do something with some equations, what do we do to show it? We plot it. We make a plot. So why not just start with the plot, right? So we're going to do Mohrs Circle. And Professor Frank, if you're watching this, tough luck. So what did we do last week? We had this crank, right? And so we looked at a couple different places on the crank. We looked at this spot up here on the top. We called that location A, the top fiber, right? And we wound up with some different stresses that resulted. All right, first of all, some normal stress, right? Where did that normal stress come from? The normal stress came from bending, which was due to this 1,000 Newton force, right? Times, we have the 100 newtons there, or 100 millimeters there, and 200 millimeters there. So this is from the moment of 1,000 newtons times, was that 100 plus 200 is 300. Even Professor Frank could do that one, right? And remember, I mentioned this last time, but newtons and millimeters are really convenient because they give us, when we wind up with newtons per millimeter squared, it winds up being megapascal. So this comes from here. So we have this 206 megapascal normal stress from the stretching of those top fibers, and that's normal stress. We also have this shear stress here, right? Now, what did that result from? That also resulted from this 1,000 newtons, but this time, this is the moment arm, right? So this is from a torque. Right? Oh, so I better take a quick second to just talk about that. See, it changes the camera depending on how long I do that. Let's talk very quickly about a torque versus a moment. This is a moment, all right? Because we even Alston and I get a little confused about this one sometimes. I wonder if we could back up a little bit. Got my office chair in the way here. So when I bend it like this, it's a force times a radius, right? A radius cross force, actually. And when I do the right-hand rule, radius cross force, my bending moment is this way. It's coming at you, right? So when the bending moment, right, which is really a force and a moment, force and the moment arm this way, the moment vector comes this way. So when the moment vector goes this way, it causes a bending like this. And that's a little tough to understand, right? Versus when I twist it like this, right, and the bending moment is going along the axis of the shaft, well, then we call that a torque. At least for this class, we're going to call that a torque. So moment, torque. Torque, moment. All right? Yeah, good. Just so we have that clear. All right, so back to the notes. What we're doing, where's my pencil? So this is a torque, and that was also the same 1,000 newtons. But this time times, let's see, 250 millimeters. Right, like that. Okay. So we have the stress element. This is for the top one, right? Now, what about the 5,000 newtons, right? Let's, I wonder, can I do that? If I do that like this, will that 5,000 newtons cause anything? Sure, it'll cause some bending, right there. But the bending only shows up at the sides of this crank. There's no bending stress at the top and bottom. Let's take another look at that. Why does it? I got to figure out how to make my default camera go that way, right? So the 1,000 Newton force causes bending like this, right? And so this is the neutral axis here. This is the other neutral axis, but you can see this is the neutral axis. That fiber doesn't stretch at all, so there's no stress there. All the stress is up here. Okay, so we know that. So this is all our stresses. It results, the blue one, 81 megapascals of shear stress, and then the red one is 206 megapascals of normal stress. All right, so what happens here? So the plane stress, right? If we consider that stress element that is not nicely aligned with the axis of the shaft, what are the important stresses, right? What the heck am I talking about there? I actually don't remember what I was talking about there. But here I've got another shaft, but this one, I gave away the punchline there. So if I take this thing and I bend it like this, right, look what happens to my stress element. It definitely stretched. Without a doubt, that thing stretched, right? So when I bend it, tensile there. When I bend it this way, right, oh yeah, definitely a compressive tensile stress there, right? This little thing here, I can't show you the other one because it's got to the punchline. Get yourself a pool noodle. If you struggled in 306 and you don't really get stress and torque and blah, 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 all that stuff, spend $2 at the grocery store or the hardware store, wherever, and get one of these. It really, really helps. So when I stretch it this way, right, tensile stress. When I bend it this way, compressive. When I pull on it, right, that makes... that also stretches it, right? So I can make an axial tensile stress this way, or a bending tensile stress. Alternatively, I could twist it, and look what happens to that. It deforms, for sure, right? There's a nice square element, and when I apply a torsion or a torque to this, right, there's definitely some shear stress that's happening there, okay? So, back to this example here. Back to this example. Okay, yeah, I've got some bending and I've got some shear. Now, it seems like if I'm worried about this thing failing, that maybe the bending and the shear add up somehow, right? Maybe they add up, but we're not exactly sure how, right? Or maybe if I just had pure bending, maybe that results in some shear, right? How about this? So, okay, here's this, here's one at the end in case I mounted it like this. I can bend that, right? Okay, it's compression for sure, tension for sure. But if there's pure bending, it seems like there's no way I could get some shear, right? How could I get bending that way? No, it's tensile, normal. Bend it this way, compressive, normal. All right, so I can't get shear from bending, right? Or can I? Right? Yeah, look at this one. So now, remember what happened here when I twisted it, right? Torsion, that's definitely a shear stress, right? We learned that in 307. Too much work for one credit. So bending, compression. But now, torsion, right? But now, if my stress element isn't so conveniently aligned with the shaft, right? Now all of a sudden, I put it in bending. Whoa, what does that look like? Whoa, I find this mind-boggling, right? That obviously this is tension, right? And it's a pure tensile normal stress. But if I pick a different coordinate system, if I say, oh, okay, I'm going to have my, for whatever reason, I like things, I'm an artist or something, I like things crooked. And I have my stress element that's oriented like that, and I put it under a pure tensile load, I get a shear stress out of it, right? So that tells me that shear stresses and normal stresses are very much related, right? And the way they're related is through the stress tensor, right? Now, in this class, well, as far as I know, in 306, you don't really get into the stress tensor much. It gets a little mathy. And in my opinion, you don't get enough linear algebra, but we don't have time to give you more linear algebra. So if it's, so the resultant stresses, get rid of that, go back to this. The resultant stresses are very dependent on element orientation, right? And of course, everybody remembers our old friend, that doesn't work, the unit circle, right? And this should be pretty much review for everybody, so I'm not going to spend a lot of time on this slide. You guys all know this really well, right? Oh, it's not. So this, you don't remember all this stuff, really? All the Greek letters and subscripts? Yeah, because this slide sucks, right? This is the worst slide in all of engineering, right? In fact, if you find it confusing, consult your younger cousin who is in 10th grade. Because I almost guarantee you, your 10th grade cousin could look at this and would totally get it, right? Totally. Why is that? Because when we plot the Mohrs circle the first time, right, this is called stress transformations. What we do is we take this stress, right? We take our normal stress, our first normal stress and our shear stress, and then we plot a point. We take these two things here, and then we just go over and up, right? And that gives us this point. And then from our other normal stress, right, we take this normal stress, and then that shear stress again, and then we go over and down, right? So this point goes to here, like that. And then we plot these 2 points. I plot this point, and then from that, I simply draw in my circle. Okay? And so that gives me Mohrs circle. So what? What does Mohrs circle tell me? Mohrs circle, remember, is a plot of all the possible stress straits, right? So under the same load, remember, I lost it again. It was working before. For the very same load, I can have anything ranging from pure tension or orient my element different, and I can get a whole bunch of shear and still a little bit of tension, right? So the orientation matters a lot. So how does Mohrs circle tell us this? Mohrs circle tells us this because I could say, well, this is, let's do this in red. This point here is my original stress element orientation. Right? So that's my original stress element orientation. But if I rotated it, say, some other way, right, I might get some other combination. I could get combinations of shear stress and normal normal stresses anywhere in there, anywhere on this whole circle, right? For instance, if I had pure tensile stress, right? So if I had this case here, right? Okay, let's think about this. On this axis here is sigma, and this axis here is tau. Let's pick a different black marker. So this is, I'll do this in red again. This spot right here, this is pure tension. Right? Just like that. Well, if I rotated it, right, and here, right here, this is for the same loading. This is another stress rate, a different stress state from same load. All right, so I got to separate these two here. And then that's like that, right? So I could have anything in there. It turns out that this angle here is 2 phi, right? Which means if I rotate my stress element, 45 degrees, I can go from pure tension to tension and shear, right? And it turns out that's where we get the maximum shear. Yet another formula or way to get maximum shear. So what are some other things on this thing, right? What's so confusing, right? Keep in mind this is a circle, right? So what is the diameter of the circle? The diameter is, let's see, it's sigma 1 minus, I can't really do the diameter yet, can I? No, let's not do the diameter yet. Right, let's say what's the radius? Right, we can get the radius. We'll get that first. Well, what is this spot here? Right, I need that. That's the center, right? So this is the center, which is, let's see, it's just halfway between here and here, or halfway between there and there. So this is just sigma x minus sigma y divided by 2, right? That's the center. And then let's see, we also need to get, the shear, right? Let's do that in red for kicks, right? This is the shear right here. Darn it. This is plus. The center is right there. And so the shear right here, right? The shear is, that's just the shear. Okay. And then we need to figure out, let's see, this length right here. Let's do that in blue. That length right there. Well, that's half of the difference between sigma y and sigma x, right? So this is sigma x minus sigma y over 2, right? And then if I really want to get the radius of the circle, all right, let's do that in green because I'm really interested in that. To get this radius, right? To get the radius, I'd simply use, what is that again? A squared plus b squared equals c squared. And so that gives me c equals the square root of a squared plus b squared, right? So if I want the hypotenuse of this green radius here, let's do that in green again, right? That is just the square root of a squared plus b squared. Well, a squared is this, right? B squared is this, right? And so that gives us the radius of our circle, right? All that is a circle and the Pythagorean theorem, right? but it's just done in a bunch of Greek letters. Okay, so please, please, please don't try to memorize all these stress transformation equations. They're crazy, right? Draw the circle, use your knowledge of circles and triangles, and then you can figure out everything you need to know, right? Pretty much the thing we're going to be most interested in is this spot. Let's see, how can I do that right here? So that spot right there is our location of, we'll call that tau max, right? That spot right there. So how do I change the orientation of my element such that I can get the maximum shear stress? We'll learn next week that it's shear stress that really breaks things. Okay, so let's do this. Plot 2 points. This is just a quick example. 2 points on a Mohrs circle, one for the x faces, one for the y faces. And then, yeah, so this is, I think this is called construction of the Mohrs circle, right? We'll go through this really quickly. What do? We need 2 points, right? Let's do the first point in red, right? I'm going to plot this point. I'm going to plot it at 137 and 50, right? This is 137, and then this is, oh, I got to do it in 50, like this. All right, and then I've got to plot the second point, right? And where do I get the second point? I'll do that one in blue again. It's negative 37, so this is negative 37, and then down 50. All right, so it's negative 37 and down 50, right? The key thing is you have to go positive shear and negative shear, right? I draw these 2 points. I draw my red point there. I draw my blue point there. And then that's the diameter of my circle, and I can sketch the rest of it and figure it out just using Pythagorean theorem and stuff like that, right? It's not that bad, right? It's really, people get so confused about Mohrs circle. I think it's a lot easier to think about in reverse. If you're interested in this, I'm sick of staring at pictures. If you're really interested in this, if you look back in your mechanics materials book. Yeah, here we go. This is an old one. Hibbler. Oh, this is a good book, actually. So look back at the derivation of the stress transformation equations. It's really pretty cool if you like math. And it's amazing that this guy Mohr came up with it when he was so young. But let's let Mohr do the work. Mohr figured out that with these stress transformation equations make a circle. And let's just use that fact and start with the circle and work our way backwards to get the stuff we need. All right. So that's kind of the approach we're going to take. So then we can go, the principal stresses, right? So the things we're most, like in fluid mechanics, we're actually interested in. So this is my original point, right? So this is original stress state, right? And then there's 2 interesting points that come out of that. We've already talked about this one up here, which is tau max, and then this one here, which is sigma max. All right. So how could I orient my stress element such that I can get maximum normal stress there? How can I orient my stress element to get maximum shear? It's right there. All right. And if you remember from 307, too much worry for 1 credit. And of course, we're locked out of the building. So I don't have any tension samples. But if you remember, your tension sample, right, when it broke at 45 degrees, didn't it? So even though you're pulling on it like this, pulling really hard on it like this, it broke at 45 degrees. Why is that? Because if we turn, let's see, where'd that go? That 2 phi. Yeah, 2 theta right there, 2 phi, whatever. Where'd it go? Yeah, so on the Mohrs circle, it's 90 degrees away from the original pure tensile state, which means in reality, it's only 45 degrees away from the original stress state, right? Okay, so surely you're going to have lots of questions about this. So I'm totally okay. Yeah, there we go. That's the next lecture. If you guys ping me during office hours, which are probably starting like 5 minutes ago, 10:06, yeah, 6 minutes ago. So anyway, I'm going to end this video now. I hope this cleared up Mohrs Circle, but this is going to be an incredibly valuable tool for you for the rest of the semester. So we'll see you later.